This is number 16 of the AMC 10A. The roots of the polynomial 10x cubed minus 39x squared plus 29x minus 6 are the height, length, and width of a rectangular box. A new rectangular box is formed by lengthening each edge of the original box by 2 units. What is the volume of the new box? Okay, well, this is related to something called Vietta's theorem or Vietta's formulas, right? Vietta's, which basically this is just, you get it from the fact that, well, let's say that we know what the roots of this polynomial are, right? Let's say the roots are a, b, and c. Well, we know that the polynomial has to be x minus a times x minus b times x minus c in order to make all the roots make the function equal to 0. And then we know that this term is the x cubed term, and that has coefficient 10 in this problem. So we get this. 10 times x minus a times x minus b times x minus c. Well, what happens if we expand this? We get this. All right. And this is very helpful because, well, if we have the height, length, and width of a rectangular box to be these roots, a, b, and c, and then we add 2 to each side length, a plus 2, b plus 2, c plus 2, and then we multiply these together, that's what finding the volume is. We get abc plus 2, ab plus bc plus ca plus 4 times a plus b plus c plus 8. And now we can just solve it because we know that this coefficient here, we know that this value is 39. Wait, no. Yeah, that value is 39. This value is 29, and this value is 6, which gives us that a plus b plus c is 39 over 10. ab plus bc plus ca is equal to 29 over 10. And this part gives us ABC is equal to 6 over 10, which basically means that our answer is just going to be A times B times C, 6 over 10, plus 2 times 29 over 10, plus 4 times 39 over 10, plus 8. And 8 is just 80 over 10, you could just say. Okay, and now if we just simplify this, well, this 2 times 29, that's just 58. 4 times 39, that's just 156. So we just get 6 plus 58 plus 156 plus 80 over 10. And if we add all these numbers up, we get, well, 64, 220, 300. Yeah, 300 over 10. All right, and that just gives us 30. That's our answer. All right, this is problem 17 of the AMC 10A. How many 3-digit positive integers A, B, C are there whose non-zero digits A, B, and C satisfy 0.ABC, ABC, ABC, ABC is equal to 1/3 of 0.AAAAA, right? Plus 0.PBBBBB plus 0.CCCCCC, right? Which happens as a result of this bar notation. Right? So this is 0.ABC, ABC, 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 0.AAA, right? So on forever. Okay. So there's something we quickly got to note here, which is the fact that this and this basically just 3-digit number ABC. over 999. Okay, why is the first one true? Well, the first one is true because, well, let's think about it. If we take 0 point A and we multiply it by 10, this gives us A point A, right? And if we subtract 0 point A, this gives us 9 times 0 point A, obviously, right? But this is also equal to just A, right? So basically, this is equal to A over 9, right? All right, so that makes sense. And now for the other part, for this second problem, right? I mean the second part, this part, which is the exact same steps, really. We have 0 point ABC, 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 ABC repeating, right? Well, what happens if we multiply it by 1000? Then we just get ABC dot ABC, 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 so on forever. And then we subtract 0 point ABC, repeating ABC, ABC, ABC. Well, this just gives us 999 times 0 point ABC repeating, right? But at the same time, this also just gives us ABC. So this is just equal to ABC over 999. Okay, so glad that's cleared up. Now, and actually what I'm going to do here is, because ABC represents the 3-digit positive integer, it's a 3-digit positive integer, right? A, B, and C are digits. They're not being multiplied in this scenario, which is very confusing. So I'm just going to convert it into place value right now. 100A plus 10B plus C. And this is equal to 1/3 of A over 9, which is A over 27, plus B over 9 times 1 over 3, B over 27, plus C over 27. And now we can multiply all sides by 999, which gives us 100A plus 10B plus C is equal to 37A plus 37B plus 37C. And if we subtract 37A to this side, we get 63A. And then over here, this is supposed to be plus 27B and then 36C. And then these all happen to be divisible by 9. So we divide by 9 and get this. All right, and that's it. This is the equation that this is equivalent to. And now we can solve the problem using it. So the best way to tackle this is to take it one A value at a time. So for example, when A equals 1, there's only one solution, 1, 1, 1, right? When A equals 2, there's only one solution again, 2, 2, 2, right? And it might seem like for each value of A, the only solution is A, right? If we set them all to A, that gives us the correct sum, right? And we would think, oh, the answer must be 9 then. But that is not true, because there are certain cases where we can deviate from the solution A, A, A. And the way we do that is by either subtracting 4 from the value of B and adding 3 to the value of C, or we add 4 to the value of B and subtract 3 from the value of C. And the reason why that would give us another solution is because, well, we're just adding 12 and then subtracting 12, right? So in cases where we can do that, right, where it's a valid operation, where we can basically, because the reason why we can't do it with 1, 1, 1 or 2, 2, 2, for example, is because if we did it with 1, 1, 1, for example, if we tried to subtract 4, we would get -3, and here we would get 4, right? Which isn't, it's not valid, because A, B, and C all have to be positive integer digits, which means they have to range from 1 to 9. So the first time we can actually get a solution that's different from the singular solution, well, 3 through 3 isn't the first time, it's 4, 4, 4. And the reason for that is, well, we can add 4 to the solution for B, and we can subtract 3 from the solution for C. And we get 4, 8, 1, which is our first non-repeating solution. Okay, well, we can do the same thing with 5, 5, 5. In fact, we can do 2 different ways of doing it, which is we can subtract 4 and add 3, or we can add 4 and we can subtract 3. Both barely fit within the space of 1 to 9. This one just barely scrapes the bottom, and this barely scrapes the top. So this gives us 2 more solutions. And now, finally, 666 is the last one where we can do this. Basically, we subtract 4 from here, and we add 3 to here. And this is the last solution that is different from just repeating, because 777 is now too high, right? We have to at least add 3 or 4 to one of the numbers, but that'll give us 10 or higher, which is not a digit anymore. So we are just left with 777, 888, and 999. And if you count all the solutions, that's just 9 of the repeating. These are all the repeating solutions, plus these 4, which are the different solutions, right? The ones where they're not all equal. And that gives us our answer of 13. Okay. AMC 10A, problem 18. Let TK be the transformation of the coordinate plane that first rotates the plane k degrees counterclockwise around the origin and then reflects it across the y-axis. What is the least positive integer n such that performing the sequence of transformations t1, t2, t3, ... tn returns the point 1, 0 back to itself? Okay, so this can be a very strange problem to tackle because it's a bit hard to think about, right? So like, let me try to draw a diagram and we can try to get a feel for it. And then I'll show how you can make the problem like much easier to find a pattern with. So sometimes what you can do is when it tells you this, like for example, it tells you a function that is a bunch of weird stuff, chances are some of this stuff can be removed without changing really how the function works if you change some stuff around, right? So let's think about it. Let's start with 1, 0, right? Well, now we're going to rotate it 1 degree and then reflect it across the y-axis. That gives us, well, that's not, this isn't to scale, right? That's definitely not 1 degree. But there we go. That's kind of like, it gives us this point that is 1 degree away from this axis, right? And now the next part of the function we're going to do is we're going to rotate it 2 degrees counterclockwise, and then we're going to reflect it back. Okay, well now it's 1 degree below the x-axis, right? And basically what keeps happening is if we continue this, right, we rotate it 3 degrees, now it's 2 degrees, and now we reflect it, right? Now it's 2 degrees above the x-axis, right? And of course, what we can do is we can simplify the problem by just getting rid of these rotations and instead just realize the fact that the pattern of the problem just goes, well, when we do T1, it ends up 1 degree above it, then it ends up 1 degree below it, then it ends up 2 degrees above it, then it'll end up 2 degrees below it, and then 3 degrees above it, and then 3 degrees below it, and it's going to continue like this, right? And the only time it can return back to itself is when it reaches 180 degrees or 0 degrees, right? Or 360, basically, right? Well, the first time it reaches 180, well, it's going to go like this. This is after T1, it ends up like here. And then after T2, it ends up here. T3, it ends up here. T4, it ends up here. T5, it ends up here. T6, it ends up here. And we're going to continue like this. And the first time we're going to reach the 180 degrees is all the way over here, which is, well, if we count odd numbers 180 times, we're going to end up at 359. But you might be thinking, well, we haven't reached 1, 0 yet. We're at -1, 0 now. But remember, this is us simplifying the function, right? We've gotten rid of the reflections. But if we include the reflections back, keep in mind that the way it's reflecting is that it reflects across the y-axis, and then it reflects across the y-axis again, and then it reflects across the y-axis again, like so. So basically, after it reaches this point, it will have reflected 359 times, which is an odd number of times. So it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 359, which brings it back to 1, 0. So hopefully that makes sense, and that explains why when we reach 359, it reaches the x-axis again, but it's at the opposite side if not for the reflections. But if we include the reflections, since there's an odd number of reflections, that is what returns it back to the origin. I mean, 1, 0. And that is why the answer is 359. Okay, now this is AMC 10A problem 19. Let Ln denote the least common multiple of the numbers from 1 to n, and let h be the unique positive integer such that 1 over 1 plus 1 over 2 plus 1 over 3 plus all the way up to 1 over 17 is equal to h over L17. What is the remainder when h is divided by 17? Okay. Well, first we should figure out how this ends up being h over L17, right? Well, let's try to get h in terms of itself, right? Well, L17, if we multiply by L17 on both sides, we get this. H is equal to L17 over 1 plus L17 over 2 plus L17 over 3 plus L17 over 4, all the way up to L17 over 17. But there's a key thing to note here, and that's the fact that, well, L17 is the least common multiple of the numbers from 1 to 17, which means that it's a multiple of 17, obviously, but 17 is prime. So from the numbers 1 to 16, we're not dividing the 17 out from L17, which means that all of these first 16 terms are multiples of 17. Which means that it doesn't matter for what the problem is asking. The problem isn't asking for h. The problem is asking for the remainder when h is divided by 17. And, well, these terms are all integers that are 0 in mod 17, so we don't need them if we're looking for it in mod 17. And we just get this. This is what we're looking for. We're just looking for this in mod 17. Well, now we have to find L17. But the thing is, that's a much easier process than it sounds like, because L17, well, we just need to find the highest, like for example, for 2, let's just do the process and I'll show you how to find it the quickest way. Well, for 2, what is the factor, what is the power of 2 that needs to be in L17? Well, the answer is 4, because the highest power of 2 we can have that is less than or equal to 17 is 16, right? There is no point in having 2 to the 5 because the smallest number that would need to have 2 to the 5 is 32, which is way higher than 17, but 2 to the 4 is necessary. So 2 to the 4 is necessary and it is sufficient, which means 2 to the 4 is the first term in our prime factorization, right? And now we move on to the next prime number, which is 3. And the highest power of 3 is 9. That's the highest power of 3 that stays less than or equal to 17, which means 3 squared is a part of our product. Right? And this all makes sense, right? Because we're looking for a prime factorization like this. And the reason for this is because if we find for each prime the highest power less than or equal to 17, then that means that there can't possibly be a number that doesn't divide L17, because that would mean that it would have more prime divisors in one of these prime divisors. But that would imply that it's larger than 17, because even just a prime power by itself would be greater than 17. So now if we continue, 5 squared is too large for 17. 7 squared is larger than 17. 11 squared is larger than 17. 13 squared is larger than 17. And finally, we end up at 17. And this is what L17 equals. So we're done now, basically, because L17 over 17 is this whole product just without the 17, right? And now we just need to find that in mod 17. So this is our answer, this in mod 17. All right, so now you can just repeatedly multiply and take modulars until you get the answer. I'm just going to try to do it the fastest way possible, which is 7 times 11 times 13 equals 1001. This is 16, this is 9. 9 times 5 is 45, which is, well, 17 times 3 is 51. So this is actually -6, and this is -1, which means that this whole product together gives us 6006. And if we divide 17 into 6006, we get remainder of 5, and that's our answer. Right. Now, this is AMC 10A, problem 20. A 4-term sequence is formed by adding each term of a 4-term arithmetic sequence of positive integers to the corresponding term of a 4-term geometric sequence of positive integers. The first 3 terms of the resulting 4-term sequence are 57, 60, and 91. What is the 4th term of this sequence? A, 190, B, 194, C, 198, D, 202, E, 206. Okay. Well, let's try to define this sequence, these sequences. Well, for the geometric sequence, it goes A, and then AR, and then AR squared, right? And then the next term would be AR cubed, but we don't need to write that. And then for our arithmetic sequence, let's just write B, and then B plus D, and then B plus 2D, right? So this all makes sense because geometric sequence, we're multiplying by the same consistent ratio, right? A, AR, AR squared. Arithmetic sequence, we're adding the same difference D. B, B plus D, B plus 2D. So the key thing to notice in this problem is that it is, even though we could try to just set everything equal and try to solve for them, what's actually like key to notice is that we have 4 variables and 3 numbers given that define them, which means we only have 3 equations to define these 4 variables. So this isn't actually a solved equation right off the bat. This is actually just it's a Diophantine equation, which means it's working in the integers, and it's working in the integers, in the positive integers, that gives it a solution, right? So we have to get clever. We can't just like force solve it because we only have 3 equations for these 4 variables. So the clever thing to notice here is that the common difference is AR minus A plus B plus D minus B, which is just D, is 3. And AR squared minus AR plus D, like, because this difference is also D, is, well, 31. And now we can do something really clever, and we can subtract this equation from this equation and get AR squared minus 2AR plus A is equal to 28. And this is very clever because this can be factors as A times R minus 1 squared is equal to 28. And this already gives us very few solutions, right? Because, well, A is restricted to the positive integers because A has to be a positive integer because A itself is a term, and R has to be a positive integer because if R was not an integer, if R was not a, well, technically R doesn't actually have to be an integer, but because A is an integer and 28 over A is an integer, that means that over here, R minus 1, basically R would have to be an integer, because if it's not, then it would not make sense. Basically, anyways, the point is that we can try different integers A that divide 28. And the only ones that can work are if A equals, well, 28, and then R minus 1 is equal to 1, right? Which makes R equal to 2, or A is equal to 7 and R minus 1 is equal to 2. Yeah, which makes R equal to 3. And these are the only 2 solutions. And if we try the first one, A equals 28 and R equals 2, we'll see that it doesn't work. And the reason why it doesn't work is because, well, these numbers, right? The arithmetic sequence actually works just fine. Everything works perfectly, except for the fact that -21 is not a positive integer. It's a negative integer, which contradicts with the fact that they're all supposed to be positive integers. Other than that, everything works, right? All the sums work and they're arithmetic and geometric sequence, but it just doesn't work like that. So this solution can't work. But if we try this one, we get an answer, which is 7, 21, 63. And then over here, the arithmetic sequence is 50, 39, 28. And this is what we needed, right? Because these sequences are all positive integers. And now we can just solve for the fourth term of the sequence. 7, 21, 63 becomes 189 on the next term, and 50, 39, 28 becomes 17 on this next term, and summing the two of these numbers up gives us 206. All right. So this has been the AMC 10A problems 1 through 20. And if you want more practice with problems of these difficulty, you can get these MathTopia books on Amazon to improve your problem solving skills.